Hi! This episode was inspired by the encounter I recently had at the Bydgoszcz University of Science and Technology. One of my students was working on the project and his machine learning model obtained unbelievably good results. It scored 100% classification accuracy on test dataset. Since my student is quite a reasonable person, his first instinct was, I made an error in the code. Unfortunately, this is quite realistic approach to the phenomena of very high accuracy in the test dataset. It is quite often indication that certain errors were present during data analysis. However, my student spent countless hours looking for a bug and he didn't find it. So, the question is it possible that the code is correct and the results are simply this good? Seems unlikely, but sometimes it happens. And when it happens, it would be nice to have some methodology for confirming that it wasn't the bug. After all, it is a problem that at least once in a blue moon every scientist has. So, I thought it may be a good idea to share how I deal with this issue. Okay, so lecimy z tematem. In step 1, I constructed a toy dataset using a deterministic algorithm. The algorithm for dataset creation will be revealed later. Step 2 is the standard division of the dataset into training and test sets. Nothing fancy here. In step 3, I created an artificial intelligence model to find the patterns in the aforementioned toy dataset for classification purposes. In this example, I chose a decision tree because it is a quite simple dataset and there is no need for anything more complicated. As you can see, the resulting accuracy is at 100% on both train and test datasets. Now, the question is there a bug in my code? Or is it possible to achieve such precise classification? Now, of course, it is possible that I made no error in the code, but the pattern allowing classification must be trivial to have such a high score on the dataset. It must be, otherwise the effects of randomness would diminish the classification results to more probable results like 96%. Unfortunately, the interpretation of machine learning algorithms is a challenging task. In fact, it is that difficult that they are considered black box models. Of course, the decision tree classifier selected for this task is not that complicated and can be interpreted directly by humans. However, I would like to show you a more generalistic approach suitable for more complex algorithms like XGBoost or neural networks. So, for the sake of this example, let's assume a lack of ability to determine the algorithm's decision-making process. Fortunately, you can determine the importance of input data. Importance is a measurement of how much the model relies on a piece of information. In the classification task using a 2D CSV style array, the model associates specific importance with each column. So, we would like to find out which column is the most important for the decision-making process of our model. There are numerous feature importance detection algorithms which are both generalized and dedicated to the particular machine learning algorithm. In this example, I chose the built-in computation method of sklearn implementation of the decision tree algorithm. As you can see on the importance chart, the model only considered the column of index 11, the last one. No other columns were deemed necessary by the model. It is quite fortunate because statistical analysis of one-dimensional samples is easy. But before we start statistical analysis, it is an excellent practice to try to visualize the data. I made scatter plots with values of the last column on one axis and classes on the second. The results are straightforward. We can easily separate types by defining divisions. If the value of the last column is below 5, then the sample belongs to class 0. If the value is above 15, then the model belongs to class 2. In any other case, it belongs to class 1. Wonderful! But for formality's sake, let's perform an ANOVA analysis to see whether the test considers the sets separable by statistical significance. As you can see, the p-value is orders of magnitude smaller than even the most rigoristic alpha parameter. ANOVA analysis confirmed our hypothesis that the value of the last column could trivially separate sets. If we can classify the samples solely by checking this value, then particular classification task may be trivial. As a result, it is quite possible that our code doesn't have errors and the 100% accuracy score on the test samples is not a bug, but an indication that our task is trivial. Of course, it is possible that the error was encountered during the creation of the dataset. For example, the measurement devices were not appropriately connected, but we can be sure that no significant bug is present in analyzing data code. Now, I'll show you how I constructed the dataset. As you can see, I made 11 columns by drawing samples from a normal distribution. As a result, these columns didn't have any meaningful information and were discarded by the model. However, the last column was created by multiplying the class integer label by 10 and adding a value drawn from the same Gaussian distribution. As a result, we obtained values with certain randomness, but still easily separable. Of course, the problem I depicted in this short clip is rather simple. After all, it all came to analyzing just one column. In future episodes, I would like to delve deeper into the more complicated examples involving patterns of multidimensional interconnections between data and maybe even how to interpret models performing image or signal analysis. Let me know if you are interested in such a content. In case you find it at least somehow interesting to watch this clip, please consider leaving a like, maybe even subscribe to see more AI related content. As for now, it is the end of the episode. Thank you for watching and good luck with your research.